Bassa-ML. This is the work we present in the CCNC 2022. With this research, we propose blockchain and model card integrated coordinatorless federated learning provenance platform. These are the authors of this work: Iranga Bandara, Sachin Shetty, Abdul Rahman, Ravi Mukumala, Juan Shao, Su-Ping Liang. First of all, I will give a bit introduction about me and some background information. I'm Iranga Bandara, working as a senior research scientist at PMAS, Virginia, US. I involved with various research on blockchain, distributed systems, cybersecurity, machine learning, federated learning, and 5G areas. One of our main motivation of doing research is we always try to do research and apply this research into live or real world applications. So Bassa-ML is one such real world platform that we have built based on our research. I'm available on Twitter. This is my Twitter username. If you want, we can contact via Twitter as well. Okay, now let's look at some background information about federated learning and model card and some technologies we are using with this research. Federated learning, it's a distributed or decentralized machine learning model. With federated learning, there are multiple clients involved with the system, and there's a centralized server which call it aggregator. Client have their own data set. What server does is server initialize some model with model parameter, we call it initial model, and distribute it to the clients. Then client train that model with their own local data set. In that case, the data not need to be shared with any third party. Data can be kept with clients, and then they train the model with their own data set, and then resend back to the server. Then server average each and every models we generate by the client and generate the global model. Then server again send that average global model to the clients. Client can retrain it. This happens in several iterations until we get in the more accurate model that called federated learning. There are some main advantages of federated learning. It preserves users' data privacy and do not share data with any third party. Data can be kept with the users and train them. Can withstand massive number of clients with limited availability, and also it handle unequal amount of client data. The federated learning can be identified as a decentralized machine learning, which is designed to address the privacy issues in the centralized machine learning system. Transparency and provenance of the machine learning models are important aspects of the federated learning system, since they impact with the lives in various domains. One of the main concerns is most of the existing federated learning systems deal with centralized coordinators, which are vulnerable to attacks and privacy breaches. And also they do not support any standard transparency and provenance mechanism for the result in the models. Those are the major concerns of the federated learning. With this research, we have proposed a model to address these issues. We propose blockchain and model card integrated coordinatorless federated learning system called Bassa-ML. Main goal is to enhance the privacy and provenance of the machine learning models. In here, model parameter sharing, local model generation, model average, model sharing functions are implemented using blockchain smart contracts. There's no any central coordinator like traditional federated learning system. We delegate this coordination into a different number of nodes. So there's a consortium of coordinators. The generated models, model training information, and model reports are stored in the blockchain ledger as model card objects. So we use model card objects to handle the data provenance. All the information related to the federated learning process are recorded as a model cards. This results in the enhanced transparency and auditability to the federated learning process. Model cards can provide a structured framework to reporting the ML model provenance, model usage, and evaluation. Basically, model card can be encode contain It can contain details about the models, suggest the users, limitation, benefit for the developers, regulators, kind of information. Basically, we can embed quantitative informations of the models as well. Google provided a toolkit called Model Card Toolkit with Google TensorFlow framework. So we use that framework in this Bassa-ML platform to generate the model cards. Our contributions. These are the main contribution. We propose blockchain-enabled coordinatorless federated learning system. The ML model parameter sharing, model training, and averaging functions are implemented with blockchain smart contract. We added more transparency and provenance to the federated learning process by storing model information and model reports in the blockchain ledger as the model card objects. All the steps related to the federated learning and all the model informations are encoded as model cards and stored on the ledger. Further, we provide a mechanism to integrate machine learning models with blockchain smart contract to do the predictions on the real-time data. Bassa-ML platform integrated with the healthcare domain. As a use case, we propose diagnosis of accurate information of bladder scenario with federated learning approach on top of Bassa-ML. Now let's look at the architecture of this proposed system. So this is the architecture. There could be multiple peers in the network. Each peer can have their own blockchain node. All the ledger functionalities, basically federated learning functions, model card generating functions, all the things are implemented on top of blockchain smart contracts. There's a peer-to-peer communication between nodes as well. In each blockchain node, it contains two services, federated machine learning service and model card service. Federated machine learning service supports to do the all federated learning functionalities, basically local model generation and global model averaging functions. Model card service handles all the model card related functionality, basically generating model cards and stored on the ledger. That's the high-level architecture. I will explain more detailed information about this, each and every component in the implementation section. Functionality. There are 5 main functions in the system: identity registration, training pipeline initialization, local model generation, global model aggregation or averaging, and real-time predictions. Identity registration. Basically, multiple peers can be collaborated in the network in the federated learning environment. Each and every peer can have their own blockchain node. When onboarding a peer, these peers' identities need to be registered in the system. So that's the way it works. Then training pipeline initialization. In federated learning environment, first the machine learning pipeline need to be initialized with the model parameters. So initially we need to generate a model and we decide the model parameters. Then what does it? Each peer will train the model with their own data set. Finally, these generated models will be averaged into global model. That's the nature of the federated learning. In Bassa-ML federated learning environment, the training pipeline initialization will be done when generated the initial block. One peer will be chosen to generate the initial block. It's the coordinator on one iteration. That peer will generate the initial block and model parameters. Training pipeline contains initial model parameters, and participating peers. The initial block will be generated by the leader peer who is chosen by the blockchain consensus algorithm. This is the way. So assume that 5 peers in the system. One peer will be chosen in each iteration to generate the coordination. So there won't be any centralized coordinator. Each peer can be a coordinator. So the coordinator will be selected by the consensus algorithm. What it does is generate the initial block with model parameters. Then it publish this block into the ledger. Then other peers can take the model and model parameters for this block. That's the idea. Now then local model generation. Once initial model and the model parameters are published, other peers in the network take this model and train this model with their own data set. their own data set resides on the off-chain storage. Then build models and model informations are saved in the blockchain ledger as model card objects. Model card objects encoded into the blockchain transaction. Once local peers generate their local models, the model informations encoded into model card object and published to the ledger. Basically, model card object contains model information, participating clients who generate local models, who aggregate it, model generation times, and also the quantitative analysis of the model can be encoded into the model card object. This is the way. Now, this is the first initial pipeline initialization process. Then other peers, what does is they take the initial block, then they take the initial model and model parameters. Then they train this model with their own off-chain storage dataset and generate a local model. Each and every peer does this operation. Once generated the model, local model, the model informations and quantitative analysis of this model encoded into model card object and published to the blockchain ledger. Then it will be visible for all other parties. Okay, then global model aggregation or average. Now assume all the peers build their local models with the data on the off-chain storage. Then coordinating peer will be aggregated or average these local models into global model. The block generation peer or coordinator will take the local models information each peer and average them according to the SGD algorithm. Then once average the local models and outcome is the global model, the coordinating peer encodes the final model information with the model card objects and saved in the block. Then finally, block with the global model will be broadcast to other peers in the network. This is the way the coordinating peer, who is the leader, take the local models generated by the other peers and average these local models in the global model. Then regarding this global model, it generates a model card object and saved in the ledger. Then other peers can fetch this global model from the block published by the coordinating peer and validate that block as well as the global model. That's the global model averaging function. Model cards. Model card object contains model information, participating clients who generate models, who aggregate it, model generation times, as well as quantitative analysis. That means all the provenance information we encode into the model cards. This is some example model card in the Bassa-ML scenario. It contains all the model information, consideration, and also we can embed the quantitative analysis of the model as well. So the parameters are variable, so we can add different parameters. So model card toolkit provides different kind of parameters which we can embed into the model cards. Once this model card is published, it can be visible to other parties in the network. So all the data provenance of the federated learning process can be verified by using the model card. Real-time predictions. We support to do the real-time predictions by using this federated machine learning models as well. The generated machine learning models can be integrated into blockchain smart contract to do the predictions based on real-time data. It adds more trust to the blockchain applications while preventing attacks such as misrepresented or spoofed machine learning model iterations. So that's the thing. So this is the way it works. So the federated model learning, these are the models which trained by the federated learning pipeline. These model functionalities can be integrated into smart contracts. Then with real-time data comes, we can use these functions to do the predictions which relate to the real-time data. If any suspects activity happens, we can notify it, and all the outcomes we can publish to the analytics storage as well. That's the real-time predictions. Now let's look at the implementation details. As I mentioned, this is the high-level architecture of the implementation, multiple peers are in the network. Each peer has two services, Federated machine learning service and model card service. All the functionalities we implemented on top of smart contracts. There's a peer-to-peer communication channel in the networks as well, so which can use to communicate with each and every node. We implemented this platform on top of Rasa blockchain. All the ledger functionalities we implemented on top of Rasa blockchain. Rasa is another research work we have done in the blockchain and enterprise level application domain. With Rasa, we trying to build a blockchain system which targeted for highly scalable enterprise applications such as big data, IoT, cloud application, banking, healthcare kind of applications. All the Bassa-ML functionalities we implemented on top of Rasa blockchain. Uh, the smart contracts of the Bassa-ML platform implemented on top of Rasa blockchain's Apple smart contract platform. Rasa blockchains comes with uh, uh, actor-based functional programming and actor-based concurrent transaction-enabled smart contracts platform. All the smart contracts on the Bassa-ML we implemented on top of Apple's smart contracts. Federated machine learning service implemented with PyTorch and PySwift based Python libraries. Model card service implemented with TensorFlow model card toolkit. There's a peer-to-peer communication between the system. So we have used Apache Kafka for the peer-to-peer communication between peers. We support to deploy this system with Docker Kubernetes and help charge-based container orchestration system. That's the deployment information. Yes, so that's the main details about the implementation of the Bassa-ML platform. Okay, that's it from my side. If you have any questions, we can discuss them now. Okay, thank you very much for your valuable time.